Okay, so what we'll do is, last lecture, what we did is we ended up doing the Carnot and the Otto cycle, and then I went over a little bit of background on just cycles in general and ideal gas power cycles. You start with ideal, then you refine your model from an ideal case, and then you better model it as the actual case, and then you really start to engineer. And then you engineer to try to make it ideal or reversible. So now I'll cover the other key cycle, the diesel cycle. And the diesel cycle represents the ideal cycle for a compression ignition engine. So compression ignition, there's no spark plug. So the Otto cycle was spark ignition. Now I have compression ignition. So compression ignition. So basically, you compress something to the point of auto ignition. So if I take a banana and I put it in a piston cylinder exposed with air, and I compress the pressure, I increase the temperature and pressure of my banana fuel air mixture, okay? And I increase its temperature and pressure large enough, the banana will combust. And then I can get work out of that system. But of course, if I have a banana engine based off of the compression ignition process, I have to keep on loading in bananas, right? So it's bananas, whatever. So you might have heard of these you see these prepper shows where they talk about the end of the world, and then somebody buys a military diesel, and then they go and find every single bit of used oil out there, and they have that stored in gallons because all they need is dirty fuel to get the engine to run. Because that military diesel engine gets things to really high temperatures and pressures, so you get auto ignition of pretty much almost anything they put in. They put a lot of organic stuff in, so they could put bananas in their fuel. Okay, so they could. Mm-hmm. And this represents, and like the question, just in wording what the four-step cycle process is, and then there's questions A, B. So let's just do A and B first. And so I have a PV diagram, and I have a TS. And so I have to start at a state. So we usually say the initial state is state 1. I could make it state 0, but we usually say state 1. And the process to go from state 1 to state 2 is isentropic compression from bottom dead center to top dead center. So if you look down a little bit more, for bottom dead center represents maximum volume of your gas power piston system. So here's my bottom dead center, and I have compression to top dead center. And so I can just go over here, my piston system, just as an example, we can go through this. This right here would represent top dead center, and then in this case, bottom dead center. Well, actually, this should be top dead center. So maximum volume, small. So I start, and then I need to just pick a spot on this graph. I'll call it V1. And so I need to pick somewhere on here along this line. So where should I start? Bottom. Okay. So we'll call that state 1. And I have isentropic compression. So to top dead center. And this is going to be my specific volume, or my volume at state 2. And I have compression, so I know I'm going in this direction. Now I want to know, does the pressure increase or decrease as I do this isentropically? So even if my diesel engine is not represented by an ideal gas, I can just use the ideal gas law to give me the phenomenological trend. Question?
Shouldn't V2 be E's?
What's that?
Shouldn't V2 be bottom dead center instead of
Well,
V2
I guess
top dead center?
State one.
And state 1 should also begin at bottom dead center.
yeah. I had it right the first time, but then I was thinking of it wrong. So this should be bottom dead center
That's correct.
and top dead center. So that's part of it. So bottom dead center. Smallest volume. Well,
Bottom dead center is at the bottom, so the volume is the biggest.
yeah. Okay. That's one way to look at it.
Just to avoid confusion, can we do like we did on the previous problem, where you just put which one was Vmax and Vmin? Or you-
I tried to introduce for those who like engines top dead center and bottom dead center, but then I end up just making it confusing.
I like Vmax and Vmin.
Vmax, Vmin. Okay, sorry about that. So I have state 1, I'm gonna go, everybody said pressure increases. So I'm just gonna say I go from pressure 1 to pressure 2. It's a little too sensitive. So then I have some process that looks like this, and really it has a little bit more curvature, but we'll leave it as such. And so I did something like that, and so now this process is isentropic compression. Let's just turn this off again. Okay, so I'll just not use the microphone. So I have, everyone can hear me? State 1 to state 2, this is P2. I have isentropic compression from bottom dead center to top center, or from Vmax to Vmin. And then the next step from state 2 to state 3 is constant pressure with heat addition. So I know I have constant pressure with heat addition, like such. So constant pressure, right? Heat addition. So then, do I increase or decrease the volume? And again, in principle, it's constant pressure, so I'm going to be along this line. How would I know which direction I go? I can write out the ideal gas law. PV equals mR gas. T, if I add heat, what should happen to the temperature? Should go up, constant pressure. T increases, V increases at constant pressure. So even if I do not have, if my diesel, right, fuel with air is not an ideal, cannot be represented as an ideal gas, this law gives me the trend. And it's going to work. I can use this ideal gas law to describe the trend of a solid. And it's going to be pretty accurate. It's just this gas number, this constant, is going to be fudged, and it might not be a constant for a solid. But this constant is similar to what you saw when you did dynamic stuff and you looked at the spring constant. So it's kind of analogous to a spring constant. Yes?
So I assume the state from 2 to 3 is that like quasi-instantaneous compression, and it ignites and it blows up. So then does that mean once it comes and ignites, there's a drop in the cylinder per se?
Okay, so I'm glad you asked that question. So the question is, it doesn't seem right, this type of drawing. I'm compressing to auto ignition, but then I'm not getting an increase in pressure. All I'm getting is this instantaneous increase in volume at constant pressure. Now really you should compress it, you get combustion, an increase in pressure, an increase in temperature, and so you would expect some 3 above.
Like an auto cycle.
Like an auto cycle. This is the ideal diesel cycle, not the real diesel cycle. Now there's something in the textbook called the dual cycle, which combines in this region the auto and the diesel, which better represents the diesel engine. I'll draw that after I finish all this. Okay, after I do these two diagrams, I'll draw what the PV diagram looks like for a more realistic, ideal compression ignition engine. But this is the ideal diesel cycle. There's other diesel cycles that you could use, and one of them is called the dual cycle.
So an ideal car, diesel car doesn't really follow this per se.
No, because I'm using all things that can be described simply mathematically. So, but we can make remember when I said you start with ideal, and you make refine the model, refine the model, refine the model, and at some point you reach more of an actual. So I could add one more process in here to make it even better. One other step in this cycle to make it even more realistic, and that's what the dual cycle does. So let me finish this, and then I'll draw what the dual cycle looks like. So I go from 2 to 3, and this one is constant pressure, and I have heat addition. I'm gonna drop my pen again. No. So I have heat addition. So I have some Q in. And then the next isentropic expansion from V3 to V4. So this is P2, P3, and this is V3, V3 to V4, and then constant volume with heat rejection. So my V4 ends up being right here. So constant volume heat rejection, and in this case I have some heat out. And this stage here is isentropic compression. And if I look at this PV diagram, it's clockwise, so it's network out. Well, this is a gas power cycle, it better be network out, right? Okay, so just related to this, what I'll do is I'll show you what the dual cycle looks like, which is more realistic to, and I'll just put it in green. And so what it does is it breaks down, it still models this stage to stage 2 as isentropic compression, but then there's auto ignition, and you get something that goes up to some stage, I'll just put X here, and then it goes over, and then it comes down. So this one is dual, and I have heat in both of these. And if I were to plot, so you can kind of see here, now when I get auto ignition, I get an increase in temperature and pressure, and a really quick one such that there's no change in volume, and then I get with additional heat in, and then the rest of the power stroke, which can be looked at as isentropic compression. Now, I'll put on here in blue what the real diesel cycle looks like, and it looks more something like this. And this region down here represents my exhaust and my intake, and so you can see it's counterclockwise. So there's network in to exhaust and put new fuel in, and then this is my power stroke. So you can see here I have something that looks like this. And so this curved line is more realistic to the actual, this is more of the actual system, and you can see the dual cycle is a better representation than the ideal diesel. Now, of course, I could do a lot of refinements to this and break it down into 50 different ideal processes to better approximate my actual cycle. But do we really want to break it down to 50 when all we really need to know is, just the general in this class? If you're going to work for Honda or some other company, then you'll do that, and you'll use computers, right, and software and all this other stuff, and talk to engineers, and you'll go all that process. Question in back?
3 to 4 is expansion, right?
3 to 4, yes. That's expansion. Yeah, 3 to 4. Thank you. Was there another question? Was that the same thing? Yes?
I was going to mention something. Shouldn't the diagram of the top dead center and bottom dead center be switched around? Because bottom dead center...
Yeah, let's cross this out. Okay, I wrote that wrong. I did it wrong. And I had some stuff wrong. So I made a mistake, and Okay, so this is my PV diagram. So then it's the same thing. I need to pick a location on my TS diagram to start at stage 1. So where should I start? Okay, someone said bottom left, which is the best way to do it. But low pressure, low temperature, what does that usually mean? Low entropy. So low temperature, low pressure, low entropy. Right? And if you can't remember, how does entropy depend on temperature? Remember the third law of thermodynamics. As I take a system, homogeneous system, in complete, internal equilibrium, and I take it to absolute zero, the entropy approaches 0. So decrease the temperature, entropy decreases. So low pressure, lower entropy. So we'll start here. And then isentropic compression. So this is pretty straightforward. I either go up and down along a straight line, and I know it's isentropic, so there's no heat transfer, and there is no change in entropy. So as I compress it, I increase its temperature and pressure. So I go up to 2. And this is isentropic. And the next, constant pressure heat addition. So constant pressure heat addition. So what should happen to the temperature if I'm adding heat at constant pressure? Just drop, so temperature should go up. What should happen to the entropy as I increase its temperature? Increase. So I can just draw something like this. And so then I have a plot like this, and it represents B equals a constant with heat in, which force the entropy and the temperature to go up. Step 3 to 4, isentropic expansion from V3 to V4. Well, it's isentropic, so I know that the entropy doesn't change. So I have S3 and S4. And then given I'm expanding it, so if I expand a gas, right, and so I'm doing this, so then it turns out similar to here, that I end up getting a decrease in temperature, and then I have this back process back, where there's heat out. Isentropic expansion. So, I'm showing you ways that you can logically use TDS relationships and PV and the third law of thermodynamics to kind of justify how temperature and entropy are related, so you can at least get the trends on these things. Now, you need to know what an isentropic process is, so you need to know that it's a vertical line on a TS diagram. Just like isobaric or a constant pressure process is a vertical line, horizontal vertical line on a PV diagram. Constant volume process is a vertical line on a constant temperature process. Same thing. Isentropic, constant entropy. So I have this, and then I can put it's clockwise, 2 letters, clockwise, 2 letters in, which implies heat net in, and of course I can relate the network out to the net heat in for a cycle. So if I go through a cycle, I'm at T1, P1, which corresponds to S1. And so I know the state of the system here. I go through my cycle, I end up back up here. I have no change in entropy for a cycle. I have no change in internal energy, but I do have heat transfer for a cycle. Is there any questions on these diagrams? I should put V constant. So I constant volume, constant pressure. Remember, it's the black one, not the dual or the... No? Question?
How did you determine which direction the entropy went from 1 to 2?
from 1 to 2. So this is isentropic, right? Compression. So I'm compressing it. And I increase the pressure. Okay? So given I increase the pressure, what should happen to the temperature? So I increase the pressure, I also increase the temperature. So 1 to 2. So isentropic compression. So I can just write PV equals M R gas T. So I increase the pressure, yet I decrease the volume. So this seems a little bit complicated, right? But I compressed it, and so it turns out that I increase the pressure more than I decrease the volume, and the temperature goes up. So when I compress it, I'm increasing the temperature. If I were to do, if for some reason there could be an isentropic process at constant volume, then it would be pretty straightforward. I would increase the pressure and the temperature would go up. You know, in some ways, sometimes it might be easier just to remember that if I isentropically compress something, I increase its entropy, or I increase its temperature. If I isentropically expand something, I decrease its temperature. So there are expansion and compression valves in systems. So if I have an expansion valve, then I'm going to have an isentropic expansion valve, then I'm going to decrease its temperature. If I have an isentropic funnel or compression valve, then I'm going to increase its temperature. So you're just compressing things, you're making it hotter. Okay, so part C. Derive the thermal efficiency of the diesel cycle in terms of K, T1, T2, T3, and T4. So I guess I didn't label these all. T1, T4, T2, T3. So T1, T2, T3, and T4. And what is K? K is equal to Cp over Cv. So it's the ratio of the heat capacity at constant pressure to the heat capacity at constant volume. And I want to know the thermal efficiency. So maybe I write this first, but in general I should have wrote the thermal efficiency is
Can you
equal
raise it a
to.
little bit?
Thank you. So the thermal efficiency is equal to the work net out over QH. Now in this process, QH is equal to QN and QL is equal to QO. I can rewrite this expression. This is the general formula for a power producing system, the thermal efficiency. Work net out over QH. Now QH is the heat being transferred from a high temperature source to my. So I have this. Another way to write this is eta TH is equal to 1 minus QL over QH, and based off the second law, QL has to be less than or equal to QH. So now I have this expression. And what I don't know is QH and QL. Now, both of these can be solved for using what? First and second law. So I do energy or entropy balance, and I can solve for QH and QL. So if I look at, let's start with QL. And QL is the heat rejected from 4 to 1. So I can do entropy or entropy balance between state 4 and state 1. Or I can do energy balance between state 4 and state 1. So let's use first law. And let's go from 4 to 1. And let's do energy balance. So I have, in general, energy in minus energy out equals the change in internal energy in my system from 4 to 1. So that's U1 minus U4, which of course is delta U. So this is just my general energy balance. Well, what is my energy in? So let's write it all out. So I have work in plus heat in plus energy associated with mass in. And of course, this is from all the work, heat, and mass from thermodynamic state 4 to thermodynamic state 1, minus all the energy out. So work out plus heat out plus energy associated with mass out. And of course, again, this is all the forms of energy, heat, mass, and work from thermodynamic state 4 to thermodynamic state 1. Yes?
Should that be U1 minus U4?
Yeah.
Before minus U1.
No, I'm going from 4 to 1. 1 is my final state. Right? I'm going from it. I'm finishing the cycle. So if I go from 3 to 4, then it's 4 U4 minus U3. But I'm going from 4 to 1. U1 is my final state. Complete the cycle. So U1 minus U4.
So, wouldn't it be 4 minus 1 then?
No,
I'm going, U1 is my final state. So
Final minus
just in general, delta U is equal to U final minus U initial. Okay? And in this case, delta U 4 to 1 is U1 minus U4.
Thank you.
And then I have that, so then I have U1 minus U4. And now I can start looking at my actual process here, and let's start crossing stuff out. What is the work in from 4 to 1? What's the change in volume? I have no work in or work out, so I can just cross both of these. It's constant volume. No boundary work. What is my heat in from 4 to 1?
No, 0.
Don't have any. What is my mass in? 0. In a real diesel engine, I might have some mass in and out. I might have a leak or whatever it might be. But in this case, we're dealing with the ideal system, so we're not having mass transfer. We're just relating it to heat in, heat out, and pressure and volume changes, right? So my heat out is QL, and my mass out is 0. So when I do all this, I get minus from over here, QL is equal to U1 minus U4. And I know that the partial of small u with respect to t at constant volume is equal to CV. So that gives me delta small u is equal to CV
Can you move it up a little, please? Thank you, sir.
delta t. And so using this, or all of this, and that, what do I end up getting? I get QL is equal to CV times, and now remember this is 1 minus 4, but really I should, let's put a plus sign here, and then I have a minus and plus. So I got QL is T4 minus T1. It's just algebra to that step. This is minus QL. QL is equal to QL. So minus QL, U4, that's my final states. Let's just make it a positive sign. And then, so delta U 4 to 1 is equal to CV 4 to 1, T1 minus T4. Well, this delta U 4 to 1 is here, but I have a minus sign, so just a sign. So I solve for QL. Yes?
Can you just explain why you don't have work out?
That's why it's nice to draw these diagrams. work is equal to the integral of P dV. What is dV? From 4 to 1. And so if I want to, this is work by, and work on the system is minus the integral of P dV. So I have that sign convention, but in either case, work on, work by, 4 to 1. There's no change in volume. I have no boundary work. And that's what the engine's doing. It's getting, right, boundary work, moving the piston. So, no change in volume, no boundary work, crossover. I don't have any electrical power inputs or things like that taking place in this problem. This ideal diesel engine is purely related to boundary-based work production. Changes in volume of the piston cylinder, right? Okay, so I did this. I got QL. Now I need to know QH. So what is QH? Well, again, I'm going to have to maybe zoom out a little bit just so I can do this in the meantime. So QH, I have heat in from 2 to 3. Now I do have a change in volume, right?
Mm-hmm.
And I do have a change in temperature, 2 to 3. I don't have a change in pressure though, so it's constant pressure. So I'm going to use the first law, and this is 2 to 3 to get me QH. And so let's do a full energy balance on that. So I got work in plus heat in plus energy associated with mass in minus work out, heat out, energy associated with mass out, equals the change in internal energy in my system from state 2 to state 3. So that ends up being, my final state is 3, so U3 minus U2. Just as a little bit of side note, U2 equals U at what? P2, T2. Remember, it's internal energy in my system, so all I need to know is the temperature and pressure. U3 is the internal energy, in this case, my ideal gas at temperature T3, P3. Internal energy at the two states. Okay, so now let's go back here. Work in. What is my work in?
No.
So I have area under the curve.
But there's constant.
So if we don't know if it's net work in or net work out during this process, what I always recommend is you choose one, and if you get the wrong sign, you know, if you get a negative sign after you guess one, you know that it was the other one you guessed wrong. Now, it turns out that when you have this expansion, it's work out. So there's no work in here, there's just work out. So I'm going to cross it out. But in general, if you didn't know, you could just guess it is work in, net work in, so then I could cross out work out. Yes?
Clockwise?
The clockwise would represent that too. So if I pick a point, clockwise from top bottom perspective. So if I'm here and I say clockwise, then this would represent clockwise from a top down. So reading the paper perspective. So if it was counterclockwise, I'd have to go this way. And I think that's fine. Like here, is it from 1 to 2? Is it work in or work out? It's work in. So all of this area here from 1 to 2 represents the work in to compress my gas to auto ignition. Then I get some work out related to that auto ignition combustion, then I would get the rest of the work out, then I won't get any. So I'd have net. So there's a lot of different ways you can find your own way to justify whether it's work in and work out, but really what that comes down to is that's going to be your personal preference. There's not one way to do it, but you need to develop your own kind of problem-solving rubric when you do these things. I can give you my kind of, ways of doing it, this clockwise, counterclockwise, to help justify you that, but at some point and tell you to use the PV, equals M gas RT, analogy, to use the third law, to use the tedious question, to use all these things to start justifying the directionality on PV diagrams. But really you need to gain practice of that on your own. And the only way to do it is by trial and error, what works best. So we're going to say that there's no work in, and we're going to assume that it's work out, and by using that top-down analogy, we could do that. What is the heat in? I have heat in. What is the energy associated with mass in? I don't have that. I don't have mass out. Okay. There's heat in, net heat in, so then and then I have this. So what I end up getting, Q in is QH minus work out equals U3 minus U2. What is work out? Well, this is work by the system. So work out equals work by, which equals the integral of P dV. And when I go from 2 to 3, it's constant pressure. 2 to 3 constant pressure. So this integral is just a constant pressure integral from V2 to V3, which then just means P2 times V3 minus V2. Right?
Mm-hmm.
So when I do this, I can rewrite this. I got QH is equal to U3 minus U2 plus P2 V3 minus V2. And it seems like we haven't got very far because I want things in terms of T1, T2, T3, T4, and the specific heat ratio. Now granted, I have QL in terms of specific heat and temperatures. I need to get this in terms of CP, K, CV, whatever. So what you need to do is you need to recall that the enthalpy is equal to U plus PV. So the change in enthalpy is equal to change in internal energy plus the change in PV, which equals the change in internal energy plus P times delta V plus V times delta P. I'm using the enthalpy relationship. Okay? Enthalpy is coupled with pressure, volume, and internal energy.
Mm-hmm.
So this right here is my delta U from 2 to 3. And this is my work part from 2 to 3. And if I look here, when I go to 2 to 3, it's constant pressure. So if this is constant pressure, this part is 0 from 2 to 3. So I got delta H 2 to 3 equals delta U 2 to 3, this part 2 to 3. And if I look at this whole segment right there, that is this. And this is delta H 2 to 3. So I got QH is equal to delta H and the partial of H with respect to T at constant pressure is equal to Cp. So my QH, or I can write it as, So I'm messing around with small h and big H. So my delta H is equal to Cp delta T, or my delta big H is equal to the mass times Cp delta T. Should put a mass up here. So end story, QH 2 to 3 is my mass times Cp, and then I go from 2 to 3, so it's T3 minus T2. So my thermal efficiency is going to equal 1 minus QL mass CV T4 minus T1 over mass CP T3 minus T2. Cross out the M's. K is equal to Cp over Cv, which finally gives me the thermal efficiency of my ideal diesel cycle is equal to 1 minus T4 minus T1 divided by K T3 minus T2. Questions? But you see how you have to play in the to do this nicely, you play around with the fact that the enthalpy is coupled to the internal energy, and we can simplify the problem. But it ties in a lot of things we've covered.
What's the difference between CP and CV?
One's heat capacity at constant pressure, one's the heat capacity at constant volume.
Okay.
And Cp for gases is always greater than Cv. Yes? What is the mass? I just kind of added it. Why? I forgot to put it in. I'm using big Q's and big W's and everything. So really there's small h, which is the enthalpy per unit mass. And there's a small u. So this part right here, that's small h. I could make this a big C too.
Okay, I kind of see what you're saying.
And so I like to write it like this with small ht, with small p, and then it's delta H, Cp, delta T, but then if I want to do big H, I need to account for the mass, which is right there.
Okay.
Yes?
So basically in the beginning when we did the delta U is equal to Cv delta T, it should have been delta U is equal to M Cv delta T.
If this is a big U.
Okay, gotcha. So that we just missed the mass there.
I missed it over here.
Okay.
Yeah, so make this small u, and then I got delta big U is equal to M Cv delta T.
But if we have no mass transfer, we can use
What's that?
If we have no mass transfer, we can use the little ones.
You can use the little ones. It's constant mass inside the system. Yeah.
I was wondering. Can we always assume that?
Well, if I tell for this process, it doesn't talk about mass transfer, right?
Yeah.
So for all these ideal gas cycles, assume no mass transfer. So it's constant mass.
You could just write that shit on option two.
I could write it, yes.
Like if same for us, we could just start like assuming
If there's no talk about mass transfer, it has to be constant mass,
Okay.
right? Think about what is the energy associated with mass. There's no mass in or out, so what happens to the mass of the system? It's just mass balance, right?
Yeah.
Mass in equals 0, mass out equals 0, change of mass of the system equals 0. Yes?
So if there was mass, it would mess up the efficiency.
So if there was mass,
Yeah.
it would change the efficiency.
Okay, as well as the graphs, right? The entropy graphs. and
Yeah,
the
all
graphs.
these things would change if you have mass transfer. And if you think about it, if there's mass transfer, how are you going to have an isentropic process?
Oh yeah.
You'd have to add the exact same mass with everything. So it just complicates everything.